So today we're going to go ahead and go through an introduction of forces and Newton's laws. So first thing I want to talk about is a force. So a force is either a push or a pull. And I want you to visualize that when we think about forces. It's anytime someone is pushing on something or pulling on something. Most of the forces we talk about this year are going to be contact forces. And that just means that the forces touch. There's some sort of contact between those forces. There's only one type of force we talk about this year that is not a contact force, and it is called a long-range force. And these are forces where there is no touching. So I want you to think about in your head, pause this video, think about it, and then check back in. What is a long-range force? Okay, so example I can think of is gravity. It's not necessarily touching us, but it is it's a long-range force is gravity. Another one I think of is magnets, which we won't talk about in this class at all, but it's another good example of a long-range force. Cool. So now let's go ahead and talk about Newton's first law. So I went ahead and wrote down Newton's first law. So we know an object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. Okay, so we're saying that things will just keep on doing what they're doing unless acted upon by an unbalanced force. So in this situation, we're kind of assuming for Newton's second law that F net is equal to 0, which means we'll get into this in just a second. The acceleration is 0 meters per second squared, and that means that the object is either moving at a constant velocity or the velocity is 0, it's at rest. So I want you to think about that for those two cases it involves with Newton's first law. Cool. So I think about as a classic example for Newton's first law is, let's say we have a icy rink where there's virtually no friction at all. If you hit a hockey puck, it's going to keep on going forever because there's no other forces acting on it to slow it down. Same kind of thing you think about in outer space where there's no forces acting on something. If something's going, it'll just continue doing that forever. Or if something's at rest, it's going to continue doing that forever unless some sort of outside unbalanced force acts on it. Cool. So let's go ahead and talk about inertia now. So inertia is just a tendency of an object to resist changes in motion. And I want you to think about what type of objects have a lot of inertia. Okay, objects that have a lot of inertia or are more resistant to changes in motion are larger objects. So more massive objects have more inertia. So if I think about it, is it easy to get a big truck moving, or is it easy to get I don't know, a tiny little tennis ball moving? It's a lot easier to kick a tennis ball or a soccer ball and get it moving than a big old truck kind of thing. Cool. Okay. So now let's go ahead and talk about Newton's second law. So Newton's second law is simply a net force causes an object to accelerate in the direction of the net force. So there's oftentimes a big equation that we use to represent Newton's second law. And that good old equation is just F net equals ma. And again, F net is going to be the sum of all the forces acting on something. And m is going to be mass, which we'll oftentimes measure in kilograms. And a is our acceleration, which we'll measure in meters per second squared. Cool. So let's go ahead and look at units for forces. So I always, again, to figure out units of something, I always look at the equation. So we know that F net is equal to mass times acceleration. So, okay, we have mass of something is oftentimes measured in kilograms if we're using SI units. Acceleration is meters per second squared. So these are the units for F net. We'll also use newtons, which you can abbreviate with just a capital N. So a newton is, just by definition, the amount of force needed to accelerate an object with a mass of just 1 kilogram at 1 meters per second squared. And that would be the definition of 1 newton. Okay, so let's go ahead and do a quick example problem using Newton's second law. Cool. So for this problem, a car leaves the road traveling at 30 meters per second and hits a tree, coming to a stop in 0.14 seconds. What average force does a seatbelt exert on a 60-kilogram passenger during this collision? Okay, so when we think about average force is going to be like F net. So I'm going to go ahead and first write down my equation for F net. So I know F net is equal to mass times acceleration. Cool. So let's go ahead and see what we know right off the bat. Well, it looks like we know the mass. I don't see the acceleration right off the bat. And there's going to be a lot of different ways to find the acceleration. My favorite way to find the acceleration is going to be use the constant acceleration equations. So I'm going to go ahead and write down my givens. We have VI, VF, A, delta X, and delta T. So let's see, VI is 30 meters per second. And again, do this yourself first, pause the video, and then check back in. VF, it comes to a stop. VF is 0 meters per second. Time is 0.14. And acceleration we want to find. Cool. So I'm going to go ahead and use the constant acceleration equation. VF equals VI plus A times delta T. Let's see, we get 0, 30 plus A times 0.14. Do some good old math. Oh my goodness, I love math. 0.14. And then I divide by 0.14, 0.14. And I get for my acceleration it to be negative 214 meters per second squared. Cool. So that's going to be my acceleration. So I'm moving to the right in a positive direction, but I'm going to accelerate the opposite direction because I'm slowing down in this case. Those signs have to be opposite. So now let's go ahead and plug this on in. So what? I go ahead and plug 214 in over here, negative 214, excuse me. And I'm getting the average force to be around negative 12,840 newtons. Cool. And that's kind of a nice thing about it. Like, okay, if I'm moving to the right in a positive direction, my seatbelt needs to exert a force the opposite direction to slow me down and to kind of like protect me, kind of thing. Cool.